In this video, we're going to continue our discussion on polynomials by learning how to long divide polynomials and use something called synthetic division to long divide polynomials that match a certain set of criteria. We're also going to learn about the remainder and factor theorems. So long dividing polynomials is very, very similar to long dividing numbers. It's basically that same algorithm you learned back when you first learned how to divide. It's just now we're going to have all sorts of terms with x's and powers in them as well. The best way to learn how to long divide polynomials is to just jump right into examples to see it in action. So that's exactly what we're going to do. So for our first example, I am going to take 4x to the third minus 23x plus 3 and divide it by 2x minus 5. So the first thing you do to set up the problem is you write 4x to the third minus 23x plus 3 underneath your division symbol, and you have 2x minus 5 on the outside. That 4x to the third minus 23x plus 3, that is called our dividend, and the 2x minus 5 is our divisor. Now, when you do this long division, you have to start by looking at just the very first term of both your dividend and your divisor. So I have a 2x and I have a 4x to the third. And I have to ask myself, what do I need to multiply this 2x by to get this 4x to the third? And we would have to multiply it by a 2x squared. So you write the 2x squared on the top, and that's because 2x times 2x squared will get me 4x to the third, and that's what I'm trying to find. Now's the part that's a little bit different from when we were long dividing numbers way back when you learned to do that. We have to take this 2x squared and distribute it onto these two guys. So 2x squared times 2x, that gets me a 4x to the third. So I write that down. 2x squared times negative 5 is negative 10x squared. Now's the part that a lot of people mess up. We're now supposed to subtract these two lines, but I think the easiest way to do that is to just change all of my signs. So make this one negative and make this one positive, and add the two lines together. My 4x to the third and my negative 4x to the third, they go away. Be careful, make sure you're only combining like terms. I only have one term that has an x squared. So I have 10x squared, I still have my minus 23x, and I still have my plus 3. And now we get to do the whole procedure again, except now we get to look at our 2x and this first term, 10x squared. And what do I need to multiply my 2x by to get 10x squared? Well, I'd have to multiply it by 5 and an x. So I write down that 5x, and then remember we have to distribute this. So the 5x times the 2x gets me 10x squared. Let me put that in green so I'm matching what I did before. 10x squared. And my 5x times the negative 5 is negative 25x. And now we have to change all of our signs. So this one becomes negative, that one becomes positive, and add the two lines together. My 10x squared and my negative 10x squared go away. Negative 23x plus 25x is 2x, and I still have a plus 3. And now we keep on doing this procedure. You keep doing this procedure until you have a lower power of x over here than the thing you're dividing by. So right now my powers are the same, so I can do this one more time. What do I need to multiply my 2x by to get 2x? Just 1. So I have a 1 up on top, and then we have to take that 1 and distribute onto my entire divisor. 1 times 2x is 2x. 1 times negative 5 is negative 5. Change your signs and add. The 2x and the minus 2x cancel out, and 3 plus 5 is 8. And now we're done because I have a lower power of x down there than the thing I'm dividing by. That 8 ends up being my remainder. So now the question is, how do we even write our answers to these types of problems? And the answer is everything that we have up on the top here, plus my remainder divided by the thing I was dividing by. So the way I would write my final answer for this problem would look like my 2x squared plus 5x plus 1 that I got from doing my long division. This was my quotient. That's what ends up on the top. Plus my remainder over the thing I was dividing by. So this is my remainder up here. And then the denominator here is my divisor. So your answer is your quotient plus your remainder over your divisor. All right, let's do another one of these. I'm going to write down what the example is first, and then we'll get a fresh board to actually work it out. My next example is going to be 1 minus 7x plus 5x squared minus 3x to the third plus 2x to the fourth divided by x squared plus 3. Now, before I even write this one in the correct form to do long division, I want to point out that I have this polynomial, my first polynomial here, my dividend. It's written in not the right order for long division. We want to have the highest exponent first and work down. So when I rewrite this in the proper form for doing long division, I'm going to rearrange the order of my dividend. So writing this problem so that we can do it, I'm going to have a 2x to the fourth, a negative 3x to the third, positive 5x squared, a negative 7x, and a positive 1, all divided by x squared plus 3. So when I set this up, I just took my dividend and rearranged the order, so it went from highest exponent to smallest exponent. All right. So now let's go through the long division process again. Remember, you start by looking at just the first terms. What do I need to multiply x squared by to get 2x to the fourth? I need to multiply it by 2, and I also need to multiply it by x squared. Then you take that and distribute. 2x squared times x squared is 2x to the fourth. 2x squared times 3 is 6x squared. Times, so they both become negative, and add the two lines together. My 2x to the fourth and negative 2x to the fourth subtract away. I have a negative 3x to the third. And then I have 5x squared minus 6x squared is a negative 1x squared. And I still have minus 7x plus 1. All right, so now we have to do it again, because I have a power of 3 here and a power of 2 here, so I can keep going. Look at the first terms again. What do I need to multiply my x squared by to get negative 3x to the third? I would need a negative 3, and I would need an x. And now we have to distribute. So we take this negative 3x and distribute it. Negative 3x times x squared is negative 3x to the third. Negative 3x times 3 is negative 9x. Change all of your signs and add the lines together. The negative 3x to the third and positive 3x to the third subtract away to 0. I still have a negative x squared. My negative 7x plus 9x is positive 2x, and I still have a plus 1. And I can do this again because I have a power of 2 down here and a power of 2 in my divisor, so I can keep going. Now I look at this first term. What do I need to multiply my x squared by to get negative x squared? Just a negative 1. So I put down my negative 1, and then it gets distributed. So that negative 1 has to get distributed over here. Negative 1 times x squared is negative x squared. Negative 1 times 3 is negative 3. We change our signs and add. My x squareds go away. I have a 2x, and 1 plus 3 is 4. And I'm done at this point because I have an exponent of 1 over here, but the exponent of my divisor is 2. It's greater than that, so we're finished. All that we have to do is write our final answer, which is my quotient, 2x squared minus 3x minus 1, plus my remainder, which is 2x plus 4, over my divisor, x squared plus 3. And there's the answer to that problem. All right, so this long division process, it can be a little bit tedious, but it is the same procedure over and over again. So once you have the rules all figured out for it, it ends up not being too terrible. You just have to get enough practice in. So now there are some long division problems that we can actually use a quicker form of long division on. And the quicker form of long division is called synthetic division. Now, synthetic division is very nice because it goes much quicker than traditional long division, but it doesn't work for all long division problems, which is why we still learn the long way as well. So synthetic division goes like this. So if the divisor is of the form x minus c, where c is a constant, then we can use this synthetic division. The steps for synthetic division. It sounds a lot more complicated than it actually is. Step 1 is write your C in a box. And it looks like this, C with a little box like that. Step 2, write the coefficients of the dividend including any that are 0, to the right of the box. Step 3, skip a line and draw a horizontal line. Step 4, bring down the leading coefficient from your dividend. So that leading coefficient gets written below the horizontal line. Step 5, multiply C and the number below the line. Write it in the next column above the line. Step 6, add the numbers in the column. And step 7, you just repeat until it's all finished. Then, once you're all done, the rightmost number is your remainder. And the other numbers are the coefficients of your divisor. Not the divisor, I'm sorry. Coefficients of the quotient, your answer. All right, so that seems like a lot of work and it seems like a lot of steps, but it takes way longer to write out the steps than to actually just do them. So I'm going to do an example using synthetic division to show you how much quicker it actually is. And I found that a lot of times students actually really prefer synthetic division, to the point that they're trying to use it on problems that they can't use it on. So it's very important to remember that you can only use synthetic division if the divisor, the thing you're dividing by, is of the form x minus a number. So an example using synthetic division. Let's do 4x to the third minus 28x minus 7 divided by x minus 3. So notice that the thing I am dividing by is of the correct form. It's x minus a number. The first step in synthetic division is to write that number in a box. And so it's going to be a positive 3 because remember it was x minus c. So the 3 is c. Then I'm supposed to write all of the coefficients of my dividend next to this box. So coefficient of the x cubed term is 4. Coefficient of my x squared term is 0, and that's very important. You have to remember the zeros. Coefficient of my x term is negative 28, and coefficient at the very end, negative 7. Skip a line and draw a horizontal line. Then you're supposed to bring down your leading coefficient. So you write it below the line. And now is the multiplying and adding part. Take the number below the line, multiply it by c. 4 times 3 is 12. Write it down in the next column. Add the column together. 0 plus 12 is 12. And now we repeat. The number down here times c, 12 times 3 is 36. And then you add the column. Negative 28 plus 36 is 8. 8 times 3 is 24. -7 plus 24 is 17. And now we're done. This is my remainder. This is my constant. This is the coefficient for x. And this is the coefficient for x squared. You just keep working backwards until you figure out all of the coefficients. And then we can write our final answer. The final answer would be 4x squared plus 12x plus 8 plus my remainder over the thing I was dividing by. And there's our very first synthetic division problem. It goes very quickly once you get the hang of the procedure, and it saves a lot of paper compared to traditional long division, but it can only be used on the problems of the correct form. That's really its only downfall. Let's do another one using synthetic division. So let's do -3x plus 7x to the third plus 5 plus 2x to the fourth divided by x plus 1. All right, there's a couple things a little funny about this problem. First, it doesn't look like x minus c. It looks like an x plus c. But remember, x plus 1 is the same thing as writing x minus a -1. So I can use synthetic division, and it's going to be c equals -1. The other thing that's a little funny is that my dividend here is all out of order. We have to make sure that when we write the coefficients out, we write them in the correct order. So I have to put my -1 in the box, and we start with the highest exponent's coefficient. So I would have coefficient of my x to the fourth is 2. Coefficient of x to the third is 7. I don't have an x squared, so that coefficient is 0. My coefficient of x is -3, and then I have my constant 5. Draw your line, drop down the first number, and then do the multiply and add. 2 times -1 is -2. 7 plus -2 is 5. 5 times -1 is -5. 0 plus -5 is -5. -5 times -1 is +5. Add your column to get 2. 2 times -1 is -2. Add your column to get 3. And again, this is my remainder. This is my constant. This will be my x, x squared, and x to the third coefficients. So to write the final answer out, we get 2x to the third plus 5x squared minus 5x plus 2 plus my remainder over the thing I was dividing by. All right, so that is how we do synthetic division. And it's really good to get very comfortable with synthetic division because we are going to be dividing by things of the form x minus c a lot. There's a lot of applications of that. So we're going to be doing that a lot in the rest of this video and the next video as well. So now we've learned about how to long divide polynomials and synthetically divide polynomials. Now we need to learn that remainder theorem and that factor theorem that I mentioned at the very beginning. The remainder theorem just says that if a polynomial f of x is divided by x minus c, then the remainder is f of c. So what this tells us is you can figure out the value of your function at a particular x value by using synthetic division and just looking at the remainder. And depending on the problem, it might be quicker to do it with synthetic division rather than just plugging in the number directly. So let's do an example using this remainder theorem. So use the remainder theorem to find f of 5 for f of x equals x to the 4th plus x to the 3rd minus 6x squared minus 5x minus 15. And since it says to use the remainder theorem to do this, I'm going to do synthetic division. I know it's supposed to be when I divide by x minus c, the remainder will be f of c. My c in this problem is 5. So I write down the coefficients for my function. I have 1, 1, negative 6, negative 5, negative 15. And then I do my synthetic division algorithm. 1 times 5 is 5. Add them together. 6 times 5 is 30. Add the column together. 24 times 5 is 120. Add your column together. And 115 times 5 is 575. Add the column to get 560. Now, the remainder theorem says that f of 5 is going to be the remainder. My remainder is 560. So I can conclude that f of 5 is 560. And you could check this if you wanted to by just directly evaluating f of 5 by plugging a 5 in everywhere. But since we have some pretty high powers there, you're going to have really big numbers to work with. So it's actually probably a little quicker to do it this way. So all we've been doing so far with polynomials is working with polynomials that have just real zeros and real coefficients. But everything we've done applies to complex polynomials as well. Complex polynomials have complex coefficients, and you can also have complex zeros. So even all the polynomials we've been working with could potentially have complex zeros as well. I'm going to do another remainder theorem example, but using a complex zero instead. So use the remainder theorem to determine if c equals 3 plus I is a 0 of f of x equals x to the 3rd minus 7x squared plus 16x minus 10. So the first thing I want to point out is we have a 0 if f of the number equals 0. My remainder theorem says f of c is going to be the remainder. So if this c is going to be a 0, my remainder should be 0. So let's set up our synthetic division. The only thing that makes it a little more complicated is that we're dealing with complex numbers. My c is 3 plus I. My coefficients are 1, negative 7, positive 16, and negative 10. Drop down the 1, and we go through our procedure. 1 times 3 plus I is 3 plus I. When I add my columns, remember you combine the things without i's together and combine anything with i's together. So negative 7 plus 3 is negative 4, and I still have my plus I. Well, now I'm going to have to do 3 plus I times negative 4 plus I. And that might be a little difficult to do in your head, so I would suggest you do that on the side as some scratch work. So I'm just going to do it up at the top of my board. 3 plus I times negative 4 plus I. We have to distribute. 3 times negative 4 is negative 12. 3 times I is 3I. I times negative 4 is negative 4I. And I times I is I squared, which is negative 1. Then I combine like terms. I get a negative 13 and a minus I. So that's what gets to be written down in the next spot. Now when I add my column together, the 16 and the negative 13 make 3, and I have my minus I. So now I have to do 3 plus I times 3 minus I. And again, I'll go up here just to make sure we see all of the work. 3 times 3 is 9. 3 times negative I is negative 3I. I times 3 is 3I. And I times negative I is a negative I squared. I squared is negative 1, so negative negative 1 makes it positive 1. And I get that this is equal to 10. Write down your 10, add your column, we get 0. So what does this mean? By my remainder theorem, this says that f of 3 plus I is equal to 0. And this means that 3 plus I is a 0 of that particular function. So is this a 0? The answer to that is yes, it is a 0. All right, so now let's learn about our factor theorem. The factor theorem says let f of x be a polynomial. If f of c equals 0, then x minus c is a factor of f of x. And also, if x minus c is a factor of f of x, then f of c is equal to 0. So what this tells us is that your zeros and your factors are related to each other. If you know the factors of a polynomial, then you know all of the zeros as well. And if you know all of the zeros, you know all the factors. So our first example using this example is x minus 6 a factor of f of x equals 2x to the fourth minus 13x to the third plus 10x squared minus 25x plus 6. Well, my factor theorem says that if x minus 6 is a factor of this polynomial, then f of 6 is going to be 0. So what I can do is just evaluate f of 6. If I get 0, then I know that this is a factor. So f of 6 is equal to 2 times 6 to the fourth minus 13 times 6 to the third plus 10 times 6 squared minus 25 times 6 plus 6. This equals 2,592 minus 2,808 plus 360 minus 150 plus 6. And when you add all of that up, you get 0. So f of 6 equals 0, and that means that x minus 6 is a factor. Now, if I wanted to, I could have also figured this out using my remainder theorem. Rather than evaluating f of 6 to get 0, I could have used synthetic division and see if my remainder is 0. Either way works. It still tells you x minus 6 is a factor. Let's do another example. We are going to factor 2x to the third plus 7x squared minus 14x minus 40, given that negative 4 is a 0. So what do I know if negative 4 is a 0? Negative 4 being a 0 means that x minus a negative 4, which would be x plus 4, is a factor. It doesn't tell me all of the factors, but it tells me x plus 4 is one of my factors. How do I find the other factors? Well, I would probably use synthetic division on this one so far. So let's divide my 2x to the third plus 7x squared minus 14x minus 40. Let's divide that by x plus 4. Using synthetic division, my 2 comes down. 2 times negative 4 is negative 8. Add those together to get negative 1. Negative 1 times negative 4 is positive 4. Add together to get negative 10. Negative 4 and negative 10 multiplied together gets me 40. Add them together and get 0, which is what we're supposed to get. Remember, this is supposed to be a factor, so I'm supposed to have a remainder of 0 there. So this is my remainder, this is my constant, this is my x, and this is my x squared. So what this tells me so far, my original problem, which is 2x to the third plus 7x squared minus 14x minus 40, so far I know that x plus 4 is a factor, and I have a 2x squared minus 1x minus 10 multiplied onto it. So I've got us a little bit factored, but we can see if we can factor it even more. That x plus 4 is as factored as it can possibly get. But this 2x squared minus x minus 10 can be factored more using the AC method that we talked about in a previous video. I need two numbers that multiply to my a times my c, which is 2 times -10, -20, and add up to my b, which is -1. Two numbers that do this are -5 and +4, because -5 times 4 is -20, -5 plus 4 is -1. So how I finish factoring this, I have my x plus 4, and I'm going to rewrite this other guy using my two numbers. I have a 2x squared, I have a -5x, and a +4x, and a -10. Don't forget to keep writing down your x plus 4. It's very easy to forget that. But now I need to factor by grouping. My first group, all that they have in common is just an x. So I'm going to pull out an x, and that leaves 2x minus 5. In my other group, I can pull out a 2, which leaves 2x minus 5. And remember, that's a good sign because I have a 2x minus 5 in both of them. They match. So that means to continue factoring this, I still have my x plus 4. Then I have a factor of 2x minus 5. And my other factor is x and plus 2. And that is my fully factored form of that problem. So we were able to use a given 0 to find our first factor, and then we were able to long divide or use synthetic division to see what we get, and then try to factor it even more using all of our factoring skills using quadratic equations. So it all adds up all together. We have two more examples just to finish this section up. Let's solve 2x to the third plus 7x squared minus 14x minus 40 equals 0. So this polynomial set equal to 0 should look a little familiar, and it's because that's the same polynomial we just factored in the last example. So the way I would solve this is I would write it completely factored, like we had just done. X plus 4, 2x minus 5, and x plus 2. And all of that equals 0. So then my zero product property tells me I could take each of these factors and set them equal to 0. And that will get me all of the solutions to this equation. This guy, I moved the 4 to the other side to get -4. This guy, I moved the 5 to the other side and then divide by 2 to get 5 over 2. And the last guy, I moved the 2 to the other side and get x equals -2. And I have 3 solutions there. -4, 5 over 2, and -2. All right, one last example to finish this up. We are going to create our own polynomial. So write a polynomial, f of x, of degree 3, that has zeros 1/3, square root of 3, and negative square root of 3. So all that they've given us is the zeros. Well, we know from our factor theorem that when you have a 0, c, then x minus c is a factor. So the first thing I'm going to do is write an equation for my function f of x completely factored. I have a 0 of 1/3, so that means I have a factor of x minus 1/3. I have a 0 of square root 3, so that means x minus square root 3 is a factor. And a 0 of negative root 3 means that x minus that negative, so x plus square root 3, is a factor. So now let's go ahead and distribute everything, and this should get us our polynomial. I'm going to start by distributing these two guys over here. So I'm going to do this multiplication first. So I'm going to have my f of x is equal to x minus 1/3 times, x times x is x squared, x times square root of 3 is square root of 3 times x. Then I have a negative root 3 times x. And then negative root 3 times positive root 3 is negative, and the square root 3 times square root 3 is just 3. All right, so let's write down what we have at this point. So at this point, my function, my polynomial, looks like x minus 1/3 times x squared, the positive root 3x and the negative root 3x cancel out, and I just have x squared minus 3. Now I can distribute this, and we'll see if we have a third-degree polynomial. X times x squared is x to the third. X times a minus 3 is minus 3x. Negative 1/3 times x squared is negative 1/3 x squared. And negative 1/3 times negative 3 is positive 1. Is this a third-degree polynomial? It is. It's a third degree because my highest power is 3. And it's a polynomial because I don't have any roots, I don't have x's in the denominators. All of my x's have powers that are non-negative, and they are whole number powers. I'm going to rearrange it so it's more written the standard way. It would be x to the third minus 1/3 x squared minus 3x plus 1. And this is just an example of one polynomial that's a third-degree polynomial and has those specific zeros. There are many, many others. Basically, you can just multiply this whole expression by any number that you want other than 0, and you'll get another polynomial that works. But this would be the easiest one to find, just by using the factor theorem. All right, so that is all I have for this video. In the next video, we're going to do a lot more complicated factoring, using lots of different theorems to help us find zeros of more and more complicated polynomials. And it gets a little bit tedious, but it's a good video, and I hope you'll enjoy it when you get to it. If you have any questions, drop them below, or if you're a current student of mine, you can ask in email or office hours as well, and I'd be happy to help. I'll see you next time.